For those of you who are new, you are watching Quantum ASMR. And for those of you who aren't new, welcome back. And for those of you who are subscribed to me, thank you so much. Thank you. And for those of you who aren't, please consider subscribing to get all the updates on my latest videos. And yeah, so today I was thinking about doing a just reading to you. I have my analytical mechanics book right here. Analytical mechanics book right here. And I figured just reading a little short section of this book would be good for today's video. So I think that's what I'm going to do today. So today we will be reading about one of Newton's laws. It's actually Newton's first law. I'm sure a lot of you know this already. It's the law of inertia. But there's a nice section in this book that goes over the history of it, or at least it says it does. I haven't actually read it in a while, so I don't really remember what's in it, but we'll figure it out together. So yeah, and if I feel like doing anything else, like the hand movements or anything like that, I'll just do whatever I feel like. So yeah, and again, if any of you have any suggestions, feel free to email me, Instagram DM me, or leave a comment below. And yeah, so without further ado, let's get into it. And also, guys, I'm really sad about this. When I was at home for spring break and I'm back at school now, I left my water bottle at home, so you guys won't get to see that for a little bit. But for now, this will have to do, I guess. All right, let's get into it. So it's on page 51, section 2.1. So Newton's first law, inertial reference systems. The first law describes a common property of matter, namely inertia. Loosely speaking, inertia is the resistance of all matter to having its motion changed. If a particle is at rest, it resists being moved. If the particle is in motion, it resists being brought to rest. Again, a force is required to bring it to rest. It almost seems as though matter has been endowed with an innate abhorrence of acceleration. Be that as it may, for whatever reason, it takes a force to accelerate matter. In the absence of applied forces, matter simply persists in its current velocity state forever. A mathematical description of the motion of a particle requires the selection of a frame of reference. Frame of reference, or a set of coordinates in configuration space that can be used to specify the position, velocity, and acceleration of the particle at any instant of time. A frame of reference in which Newton's first law of motion is valid is called an inertial frame of reference. This law rules out accelerated frames of reference as inertial because an object really at rest or moving at constant velocity, seen from an accelerated frame of reference, would appear to be accelerated. Moreover, an object seen to be at rest in such a frame would be seen to be accelerated with respect to the inertial frame. So strong is our belief in the concept of inertia and the validity of Newton's laws of motion that we would be forced to invent fictitious forces to account for the apparent lack of acceleration of an object at rest in an accelerated frame of reference. A simple example of a non-inertial frame of reference should help clarify the situation. Consider an observer inside a railroad boxcar accelerating down the track with an acceleration a. Suppose a plumb bob were suspended from the ceiling of the boxcar. How would it appear to the observer? And then it shows us a figure 2.1.1. So this is the boxcar and it's moving this way and it's accelerating, and there's something hanging from the ceiling as it's accelerating. So this is what they're talking about. The point here is that the observer in the boxcar is in a non-inertial frame of reference and is at rest with respect to it. He sees the plumb bob, and also apparently at rest, hanging at an angle, which they call theta, with respect to the vertical, which is just up and down. He knows that, in the absence of any forces other than gravity and tension in the plumb line, such a device should align itself vertically. It does not, and he concludes that some unknown force must be pushing or pulling the plumb bob toward the back of the car. Indeed, he too feels such a force, as anyone who has ever been in an accelerated vehicle knows from first-hand experience. A question that naturally arises is, how is it possible to determine whether or not a given frame of reference constitutes an inertial frame? The answer is non-trivial. For example, if the boxcar were sealed off from the outside world, how would the observer know that the apparent force causing the plumb bob to hang off vertical was not due to the fact that the whole boxcar was misaligned with the direction of gravity. With the direction of gravity. That is, the force due to gravity was actually in the direction indicated by the angle. Observers would have to know that all external forces on a body had been eliminated before checking to see whether or not objects in their frame of reference obeyed Newton's first law. It would be necessary to isolate a body completely to eliminate all forces acting upon it. This is impossible, because there would always be some gravitational forces acting, unless the body were removed to an infinite distance from all other matter. Is there a perfect Is there a perfect inertial frame of reference? For most practical purposes, a coordinate system attached to the Earth's surface is approximately inertial. For example, a billiard ball seems to move in a straight line with constant speed as long as it does not collide with other balls or hit the cushion. If its motion were measured with very high precision, however, we would see that its path is slightly curved. This is due to the fact that the Earth is rotating, and its surface is therefore accelerating towards the axis. Hence, a coordinate system attached to the Earth's surface is not inertial. A better system would be one that uses the center of the Earth as coordinate origin, with the sun and a star as reference points. But even this system would not be inertial because of the Earth's orbital motion around the sun. Suppose then we pick a coordinate system whose origin is centered on the sun. Strictly speaking, this is not a perfect inertial frame either, because the sun partakes of the general rotational motion of the Milky Way galaxy. So, we try the center of the Milky Way. But, to our chagrin, it is part of a local group, or a small cluster of some 20 galaxies that all rotate, about their common center of mass. Continuing on, we see that the local group lies on the edge of the Virgo supercluster, which contains dozens of clusters of galaxies centered on the 2,000-member rich Virgo cluster, 60 million light years away, all rotating about their common center of mass. As a final step in this continuing saga of seeming futility, we might attempt to find a frame of reference that is at rest with respect to the observed relative motion of all the matter in the universe. However, we cannot observe all the matter. Some of the potentially visible matter is too dim to be seen. And some matter isn't even potentially visible. And the so-called dark matter, whose existence only infer by indirect means. Furthermore, the universe appears to have a large supply of dark energy, also invisible, which nonetheless makes its presence known by accelerating the expansion of the universe. How old is this book? Sorry. Okay. 2005. Is it 2005? So, I'm going to skip the last couple pages of that section, and so because that was a little shorter, I'm gonna go ahead and go on to read Newton's second and third laws. So as far as the live stream goes, I still want to do it at the end of this week. Y'all need to give me some more times. I am in the Eastern time zone. I was thinking maybe Friday night or Saturday night. So if you guys could please either leave a comment below about if that's okay with y'all, or if you want to do it, if that's okay with y'all, or leave a comment under my last update video thanking everybody for the 1,000 subs. So let's continue. Let's continue to read. Mass and force. Newton's second and third laws. The quantitative measure of inertia is called mass. We are all familiar with the notion that the more massive an object is, the more resistive it is to acceleration. Go push a bike to get it rolling, and then try the same thing with a car. Compare the efforts. It's a lot more difficult with a car. The car is much more massive, and a much larger force is required to accelerate it than the bike. A more quantitative definition may be constructed by considering two masses, m1 and m2, attached by a spring and initially at rest in an inertial frame of reference. For example, we can imagine the two masses to be on a frictionless surface, almost achieved in practice by two carts on an air track, commonly seen in elementary physics class demonstrations. Now imagine someone pushing the two masses together, compressing the spring, and then suddenly releasing them so that they fly apart, attaining speeds v1 and v2. We define the ratio of the two masses to be m2 over m1 is equal to the absolute value of v1 over v2. If we let m1 be the standard of mass, then all other masses can be operationally defined in the above way relative to the standard. This operational definition of mass is consistent with Newton's second and third laws of motion, as we shall soon see. Equation 2.1.1 is equivalent to, and that's the equation that I just told you, is equivalent to the change in m1 times v1 equals the negative change in m2 times v2, where m1 is the mass of the first object, v1 is the velocity actually of the first object, and then m2 and v2 are the mass and velocities of the second object. Because the initial velocities of each mass are 0 and the final velocities v1 and v2 are in opposite directions, if we divide by delta t and take the limits as delta t goes to 0, we can get their derivatives. So instead of the change in, which is a little delta sign, as shown right here, you see that? If we divide by delta t and then take the limits, it changes into a derivative for each side with respect to t, which is time. The product of the mass and the velocity, mv, is called linear momentum. Linear momentum. Linear momentum. The change of motion stated in the second law of motion was rigorously defined by Newton to be the time rate of change of the linear motion of an object, and so the second law can be rephrased as follows. The time rate of change of an object's linear momentum is proportional to the impressed force, which we call capital F. Thus, the second law can be written, and then they give us a thing where it's F is equal to some k, which is a constant, times the derivative with respect to t of m times v, the mass and the velocity. So, considering the mass to be constant, independent of velocity, which technically is not true of objects moving at relativistic speeds or speeds approaching the speed of light, which is 3 times 10 to the 8th meters per second. A situation that we do not consider in this book. We can write F is equal to k times n times the derivative of v, velocity, with respect to t, and that can be rewritten as k times m times a, which is the acceleration. The constant of proportionality can be taken to be k equals 1 by defining the unit of force in the SI system to be that which causes 1 kilogram mass to be accelerated 1 meter per second squared. This force unit is called 1 Newton. Thus, we finally express Newton's second law in the familiar form that we all know. F is equal to ma, so the force is equal to mass times the acceleration. The force F on the left of the equation is the net force acting upon mass m. That is, it is the vector sum of all the individual forces acting upon m. So then we note that equation 2.1.3, which was the derivative with respect to t of m1v1 is equal to the negative derivative with respect to t of m2v2. And so that's equivalent to force 1 is equal to the negative force 2, or Newton's third law. Namely, that two interacting bodies exert equal and opposite forces upon one another. Thus, our definition of mass is consistent with both Newton's second and third laws. So, that's all they have for Newton's first, second, and third laws. Yeah, so that's all I have for you guys in this video. If you liked it, give it a thumbs up. If not, I'm sorry, but I have more videos that you can check out. I don't always do reading videos. I do a lot more, so go ahead and take a look at my channel if you haven't already and see what other stuff might be interesting to you. So, I hope you all have a good night, or a good day, or a good morning, whichever whichever time of day you're watching this. So, yeah, I hope that you guys enjoyed this video, and yeah, I love you guys, and I'll see you in my next video. So, bye.